Good morning. Today we'll see uh, an experiment on FIR low pass filter design. So before I explain the code, so we'll quickly go through this particular table, which is very important for us to understand that. So in general, we have various windows which I have listed over here. They are rectangular, Bartlett, Hanning, Hamming, Blackman window, and transition width corresponding to rectangular wind of a main lobe is 4 pi by m plus 1. Similarly, for Bartlett, Hanning as well as Hamming, it's same. It is 8 pi by m, whereas for Blackman, it is 12 pi by m. And stop band attenuation for rectangular filter is minus 21 dB. For Bartlett, it is minus 25. For Hanning, it is minus 44. For Hamming, minus 53. And for Blackman, it is minus 74 dB. And these are the relative amplitude of side lobes. They are, for rectangle it is minus 13 dB, for Bartlett it is minus 25, for Hanning minus 31, for Hamming minus 41, and for Blackman it is minus 57 dB. Now based on this we are going to write a code. So if you observe here, for rectangular window transition width is different, which is 4 pi by m plus 1, and attenuation is minus 21 dB. Whereas if you observe these three remaining window, that is Bartlett, Hamming as well as Hanning, transition width is same. So let us try to understand what is transition window. Let us consider an example of a low pass filter. So in low pass filter you have passband region, right? And if you observe in non-ideal filter, after it reaches passband, you won't immediately won't get stop band region. There is some delay associated with it, right? After some time you'll get stop band region. That particular region is transition region, if you can recollect, and that particular width we call it as transition width. And it is same for Bartlett, Hanning as well as Hamming window, which is 8 pi by m. Okay, as a result, so it will look something like this. So if I plot magnitude frequency response, if I consider low pass filter, so if I consider this region as well as this region, this is Kp, that is passband attenuation, and this is Ks, stop band attenuation, and this is omega p, passband region, and this is omega s, which is stop band region. So what we can understand from this is, from here, that is 0, this is magnitude axis 20 log h of j omega, and this is frequency axis omega. From here till here all the signals will be passed easily through this particular filter, and from here till here this particular width, see, there is no sudden transition because this is not an ideal filter. So it needs some time from passband to stop band. That particular region we call it as transition region, and that particular width is this one. The one which you can see here is this one, transition, this window. After that it won't attenuate, it will attenuate everything. Whatever may be the frequency, beyond this it will attenuate. So hope you understood the transition width here. Now I'll come out of this. So we'll try to understand the code. First three lines, CLC clear all, close all. CLC is used to clear the command window, clear all to clear workspace variable, close all to create any additional windows that has been created. FS, we are asking user to enter sampling frequency. FP, passband frequency. CR, here now we are taking transition width. And AS, stop band attenuation. If you observe here, we are not asking user to enter stop band frequency. Rather, we are asking user to enter transition width. So how to calculate stop band frequency then? Passband frequency plus transition width. You will get stop band frequency. So that's how we'll calculate. We'll see that later in the code. Moving on. So we need to normalize all the frequencies. So first one is we'll normalize sampling frequency. Fn is equal to Fs by 2. And then we'll normalize passband frequency, which is given by Fp, that is sampling frequency divided by normalized sampling frequency, that is passband frequency by normalized sampling frequency. You will get normalized passband frequency. Similarly, you normalize transition width, and then as I told, if you want to calculate stop band frequency, it is given by Fp plus transition width. You are understanding this now, right? Now moving on, we need to normalize even this stop band frequency. So which is given by Fst, stop band frequency, divided by Fn, that is normalized sampling frequency. And to get cutoff frequency, the formula is normalized passband frequency plus normalized stop band frequency by 2. So we'll get normalized cutoff frequency. Now, based on the table as I told, we'll write the code. What is AS? Stop band attenuation. So as per this particular table, this is stop band attenuation. If it is less than 21 dB, which window I need to use? Rectangular window, which is also known as boxcar window. Earlier we used to call this as boxcar. Boxcar, rectangular, both are one and the same. So here, if you observe, if attenuation, stop attenuation is less than 21, then I'll find out N through this seal of 4 by TWN. See here, now I'm making use of this seal of 4 by TWN. If remainder of n comma 2 equal to 0, that means if n is even number, I'll convert that into odd number and then I'll make end. And which window I'm supposed to use? Boxcar. Boxcar, rectangular, both are one and the same. If stop band is less than 21, as per this table, which window I need to use? Rectangular window. If you observe this, transition width is same for Bartlett, Hamming as well as Anning. So I'll club them together. Okay, you remember this 8 pi by m is transition width for all these three windows: Bartlett, Hamming. And if you observe attenuation, in Hamming I'm getting more attenuation. That means it will be my signals which is beyond my limit will be compressed more in Hamming when compared to these two. So which is better out of these three then? All these three are providing same transition width, but Hamming is providing me better attenuation. So I won't consider these two. Rather, if the stop band attenuation is more than 20 and if it is less than this, that is minus 53, which window is best? Hamming. The reason is anyway all these three windows are providing me the same transition width, but with better attenuation I'm getting if I use Hamming window. So I want to design a filter in such a way that I should get better attenuation. So in general I'll use the better one out of these three because they are all providing me the same transition width. So I'll use the same. Now you observe the code now. If AS, else if AS, what is AS? Stop band attenuation is more than 21 and less than 53. Transition width is what? It is same, right? 8 pi by m. So I'll use this particular formula. 8 by transition width. So seal of 8 by TWN, you'll get N. So check whether it is even. If it is even, convert that into odd and then N. So which window will offer me the better attenuation out of the three for this that is Bartlett, Hamming, Anning, because all three are giving me the same transition width but different attenuation. So more attenuation will be the better one. So I'll use Hamming window. So here if you observe the code, which window I'm using? I'm using Hamming window because anyway transition width will remain same, but I'll get better attenuation, which is very very important for me to design a filter. Else, which other window have? If attenuation is more than 53, obviously I need to use Blackman window. Okay, and transition width is 12 pi by m. So if you observe the remaining part of the code, so n is given by CL of 12 by TWN. Again check whether remainder is 0 or if it is even. If it is even, make it odd, that is n is equal to n plus 1 end. So in general I need to use the last window, that is Blackman window, and then end. So once you calculate which window you are supposed to use for the FIR filter, the next is to plot. So HN, here I'll use one inbuilt function, FIR1, n-1, FCN, WN are the inputs for it. So then find out frequency response, magnitude response. H comma F is equal to FRUQZ of inputs are HN, that what you found out here, 1, number of points. This is variable you can use, better the number of points, better will be your filter, and Fs. And magnitude, it is given by 20 log to the base 10 ABS of H. So once you find out these two, I'm going to plot it. Figure plot F comma H underscore magnitude, that is magnitude versus frequency response, grid turned on, X label frequency, Y label magnitude, title magnitude response. Similarly you plot phase response. So you have angle as an inbuilt function, angle of H I need to find out. So H underscore phase is equal to angle of H. Then figure plot F comma H underscore phase into 180 by pi. So because in general we'll get angles in radians, we need to convert that into degree. How? Multiply by 180 divided by pi. Grid on, X label frequency, Y label, now it is phase in degrees, and title for that is phase response. Now I'm going to run this and observe the output. So I'm going to use this as input. So sampling frequency 50,000, passband frequency 10,000, transition width 5,000, and stop band attenuation 50. Now if you observe this, so this is the magnitude response I got. So what was the attenuation I considered here? You observe this. So attenuation I considered 50. So if you observe this particular table, if attenuation is 50, can I use Hanning? No, because Hanning is offer me a maximum of minus 44 dB, but I entered 50, so I can't use any of this. That is, I can't use rectangular, Bartlett or Hanning. So which one I need to use? Hamming, isn't it? So what is the frequency response of Hamming? So the magnitude frequency response of Hamming windows will look something like this. So we're going to check the same in the output. So in the output, magnitude frequency response should look something like this. So if you observe here, is it looking like the one which is standard one? Yes, of course, it is almost same as the standard one. So through this we can observe the output that we are for the given attenuation which is 50 dB. The code which I have written is considering Hamming window. Similarly, you can select different attenuation, maybe less than 21 dB. So at that time you're going to observe magnitude frequency response similar to rectangular. Similarly, you give attenuation, stop band attenuation more than 53 dB, say for example 60 or 70 dB. At that time the last window will be considered, that is Blackman window will be considered. So based on this table only we have written the code and we are getting the proper output. And this is another response, that is phase response. Hope you have understood this. Thank you.